Hello students, welcome to the video on single replacement. Single replacement, the nice thing with it is that it's a lot easier to balance than some of our combustion and decomposition reactions, so that's a plus. When we have a single replacement reaction, we're going to have a metal that is going to react with an ionic compound. So that'll be a metal with a nonmetal. So I'm using the front letters of the alphabet to represent my metals and the back end of the alphabet to represent my nonmetals. And so what happens in a single replacement is exactly what it sounds like. A single element will be replaced. So my metal A will replace metal B, which means that now B is by itself, and now A is in a compound with X. So let's try an example. I have magnesium. It's a solid because it's in its elemental form. And so metal is usually a solid. And then I have sodium chloride, which is aqueous. And so with this, my magnesium is going to kick out my sodium. So now my sodium will be elemental sodium. It will be a solid. Plus magnesium chloride. Magnesium is a +2, chlorine is a -1, so it'll be MgCl2. Because it's a Cl2 on my product side, I need to balance it out, so I need a 2 in front of my NaCl on my reactant side, which alters my sodium, so now I need a 2 in front of my sodium. This is now my balanced equation. So that's my balanced equation. In single replacement, you're also going to be asked for ionic equations. We're going to do the full ionic first. Normally you won't have to do this step, but I want to show you step by step what's going on. So this is my full ionic equation. And so with this, what we're going to do is look through our formula and determine which ones can be broken into their ions. So keep in mind that when we have something that is aqueous, aqueous means that it's soluble and it's able to break into its ions when placed in water. Aqueous is in water. So with this, I'm going to start by looking at my magnesium. My magnesium is elemental magnesium, so straight off the periodic table. So when I take magnesium off the periodic table, when I just look at it, it's got 12 protons and 12 electrons. It hasn't given away any electrons yet because it hasn't formed a bond. So anything in its elemental form is going to be neutral. Then my sodium chloride will break into its ions. So Na. I'm going to keep my 2 out front because that's going to help with balancing later. So I have 2 Na plus 1, and it's aqueous, plus 2 Cl minus 1, and it's aqueous. I'm not going to worry that the chlorine is a diatomic. That's not what we're focusing on right now. We're just focusing on when it breaks into its ions. So sodium then, on the other side, is now my elemental sodium. I'm still going to keep my coefficient there because it's going to help with the balancing. But now, since it is elemental sodium, it's going to be neutral. Our elements are always going to be neutral. Magnesium chloride breaks into its ions. So I have magnesium, that's aqueous. That has a +2 charge, plus chlorine. I'm going to keep that 2, because again, with balancing, aqueous -1. And so with this, I have my stuff, and it's going to help keep it balanced. I have all of my ions, I have all of my state scripts. So now what we're going to do is just like in math class. If we have the same thing on both sides, it will cancel out. So when I look, for example, I can see that magnesium, I have a magnesium neutral over here and a magnesium ion over there. So that means that the magnesium is going to stay. It's not going to cross out. When I look at sodium, I have a sodium ion over here, and I have a sodium neutral over there. So again, they're not identical, so they don't cancel out. However, when I look at my chlorine, I have 2 chlorine ions. On the other side, I have 2 chlorine ions. So they are exactly the same, and they will cancel out. If they didn't balance, if I only had 1 chlorine on one of the sides, that would tell me to go back and check my balancing and my balanced equation. I might have forgotten something. So now, that's the only ion that's a spectator ion. That's the only ion that does not take part in the reaction itself. So, we're going to look at our net ionic equation. And on my net ionic equation, I'm going to rewrite my ions and neaten it up. I'm going to get rid of the ones that I crossed out. So I have my magnesium that's neutral, plus my 2 sodium ions, yields my 2 sodium neutral, not ions, plus magnesium ion. So again, this is another good point to stop and check and make sure you're balanced. I have 1 magnesium on each side. I have 2 sodium on each side. So now what we're going to do is what's referred to as a redox reaction. And my redox reaction, all I'm going to do is I'm going to take my metals and I'm going to write what they were in the reactants and compare them to what they were in the products. I'm going to do the same thing with my sodium. I'm not going to worry about carrying the coefficient. My net ionic equation had to be balanced. But for the redox reaction, I don't really care about balancing. I'm going to focus on what happened to the charges. So I'm going to have a sodium plus 1. And that's going to take me to a sodium that's neutral. By not worrying about the numbers that balance it, it also allows me to make it a little bit cleaner and neater. So now looking at these, I look and notice that my magnesium started out as neutral and ended as a positive 2. And so I am getting less negative. I'm getting further away from the negative side. And so since I'm getting less negative, that means I'm losing my negatives, or I'm losing electrons. My sodium, however, is going from a plus 1 to neutral. It's going towards the negative side. So since it's going towards the negative side, it's going to gain negatives. It will gain electrons. The reason why this is important is because when things lose electrons, it is referred to as being oxidized. When metals gain electrons, it is said to be reduced. And so a handy little way to remember this, if you so choose, is Leo, Ger. Yes, I intentionally put this little dash by a lowercase e because that's our symbol for electrons. And so Leo losing electrons is oxidized, and Ger is gaining electrons, is reduced. So lose electrons, oxidized, gain electrons, reduced. Another thing you can remember is oil rig. So So in this case, oxidized is losing, reduction is gaining. And so hopefully that has helped you on how to write a net ionic equation for a single replacement reaction. If you found this video helpful, be sure to press the like button, just so that way I know that it was helpful and it's worth my time in making them. Have an excellent rest of your day.